Hello and welcome back. In this episode, we are adding plasticity to our simulation, so we get a lot more of a gooey-like fluid. In the last one, we added our particle emitter, and now we are also combining this one with the plasticity. All right, in Visual Studio, we have to create a new class and new file, and this will be the spring for our plasticity. And in here we have the particle ID for the particle A and for particle B, and then we have a length. So let's create the class first, class spring, then a constructor. And of course I need to disable. Take it up autopilot, there we go. And then we have a particle A index, a particle B index, and a length. Then we're gonna assign these variables. And the length. There we go. This is our spring. Then, of course, we need to add this spring to our main HTML. I'm just going to copy this one and add the spring.js file in here. All right, then we have the spring. We can close that. Then we need to change something in our hash grid. Currently, we are getting from the get neighbors of particle and from the get content of cell, we are getting the actual particle. And I want to change that we only get the index of the particle. Okay, so that we can say instead of this one, we will then say this particles of this index. So this will return a index, and this index is the neighboring particle. And I want to change this so that we can use this method here because it's then simpler to use the springs. And yeah, I think it's also not that complicated to change this. We just need change this one, that it's gonna push the index, and here just that it's creating a new array out of the index. So this is a new array, and this is we will put a list into this one. Well, I think actually, one moment. Yeah, no, we don't need the extra braces. We just need this, I think. All right, and I think this is everything. I'm just gonna take a look at my reference. Yeah, that looks pretty good. All right, and then we can start implementing our spring. And for this, we need two new methods. And these two methods are called the adjust springs. So let's add the adjust springs first. Adjust springs with a delta time. And then we have the method spring displacement, which will change the position depending on the spring values for the particles. Going in the adjust springs, we will calculate the change, and here we're going to apply it. And if you look at the code, you see that the adjust springs has two two for loops, one for the neighboring particles and one for the springs. And what we are going to do is we are taking the part where we need to calculate the new length for the spring. We will take this and put that into the second for loop. Okay, the reason behind this is that in my implementations, it did not work really, but you still get the results you will expect from the paper, and also these are pretty good. So I think that's a good solution to that problem. And yeah, let's first start with the adjust springs method. We can copy quite a lot from the viscosity function right there. And I'm going to copy, let's copy step by step everything. First, we need a for loop, of course. Then we have to retrieve our neighbors. Oh, and I forgot one thing. We need to change how we retrieving the neighbors, right? This is our new method, and we need to do that in the double density relaxation too, right there. So I'm just going to replace this one, and everywhere where we get the neighbors, like here. All right, and I think that's it. All right, so please make sure you have replaced everything. And if we start the simulation, you should actually see that the fluid simulation is still working. So let's check this. Let's go to the browser, refresh, and there we go, it's still working. And that means that our small changes in our hash grid are working. Cool. Then we can go to Visual Studio again, back, and let's finish the adjust springs method. Well, or let's say the first for loop, because we need to copy a little bit more. And I'm gonna copy, and then also just comment this line here out. There we go. All right. So I'm gonna copy this line too. Paste it in there. Then, of course, we need to iterate through our neighbors. So I'm just going to copy this one. And in the for loop, we are calculating a spring ID now. And the spring ID will make sure that there won't be too much springs generated. So every particle has, every spring has its own ID, and that means just the particles won't have, there won't be too much springs for the same particles, because there might be the case that the springs are already generated or were already generated for this particle, and we don't need to generate a new spring anymore, and this step prevents that. That there are not that many springs generated. Because if we don't do that, there will be too many springs, too much force on the particle, and then probably the simulation would just explode. And of course, we don't want that. So, and the spring ID, to prevent this, we can just say particles.length, and then we have our spring ID. And then what I also forgot, of course, we have to add a new variable which stores our springs, and this will be a new map. And in this springs, we are storing the springs, as I said. And here in the if case, we are checking for if the spring ID is already there, because if it's already created, then we continue. We are not creating a new spring. And now we are creating the spring when the Q value is less than 1. And for this, of course, we need to calculate the direction again. So let's copy this one again. There we go. This is fine. Jawohl. All right, and then we can calculate the Q value, and this is just y with the length. And then if this value is smaller than 1, then we say we are creating a new spring, and this is a new spring. Oh, new spring. Come on, spring. There we go. And this will have the particle index from our current particle, from this particle here. Then with the neighboring index, this will be neighbors, and from the J value. And then our length will be the interaction radius. You can also set a smaller radius if you want, or do it like a constant. You can do that too. I think if you use a smaller radius, then the simulation will behave like a, well, it's not going to be like, how can I compare it? I would say it's not going to be like, not that, not like a goo, right? It's going to be more fluid. It's going to move more. And with a higher radius, this is the maximum radius we can set, there will be more springs, and with a lower radius there will be less springs, and the more springs there are, the more non-moving, we get a more non-moving result out of that. And then we can say this.springs.set, now we are just adding the spring with the spring ID as the key, and then the new spring. And this is our adjust springs. Well, not that. It's just one part. It's the first for loop. And now we have to iterate through all of the springs which are currently in the simulation. And for this, we can say, we can do something like this, where we can get the key and the spring out of the map. All right, and here we get the we get both particles interacting in the spring. We can do this like this: particle, spring particle A index. These are the variables in the spring, these two. And then we need to add the index for particle B. Oh, sorry, I think yeah, oh, sorry, that's not right. We need to do this for the other particle. So for the neighboring, or for the other particle interacting in the spring, and here it's particle B index. All right, then we can calculate the distance. And the distance is, again, just a subtraction from both of these particles. And this is the y dot position minus j dot position. And then we need the length of this one. Then we can calculate that d value. And here we need to add a constant. And this constant will be the gamma constant. I'm going to add a comment right there. Plasticity parameters. I'm going to add AS here too. All right. And then add the constant gamma is equal to, what is a good number? I think a good one is 0.3. And I'm going to add the other constants too. So plasticity is 1, and then we have the spring stiffness. Spring stiffness. Did I write that right? I think so. 0.9. These are my values, but feel free to test any value you like. And then we can calculate the d value. And this d value here is calculated by saying this dot gamma times the spring dot length, right? And after the d value, we have to calculate, or let's say, yeah, we have to use an if statement to check for the distance now. And here we need to check if the distance is greater than spring length plus the d value. Note that the spring length here is actually the Liy value, and I think I think I'm gonna do another variable where this is stored in that, so we are not confusing anything. And we have then the exact code for our, well, the code is just the same like in the paper. Yeah, this is the d value. Then we check if the distance, this is the Riy value, and maybe I can save this value also in a small variable for this. I'm just gonna paste this like this. All right. And if this value is greater than the L value, which is the distance, right? Yes. No, actually, I think this is this one. Okay, yeah. I think I'm gonna use y there, and now we need to check if the distance is greater than Liy plus the d value. Then we say spring dot length plus equals the delta time times this dot plasticity times the distance. And the distance is the Iy value minus the Liy value minus d. And then we can calculate the other case. Where else? Where? Yeah. One note here. This one is for the stretching, and this one is for the compression. And here we are saying if distance is smaller, than the Liy minus the d value, then we have a compression, and then you can say spring dot length minus equals the delta time again times this dot elasticity times the Liy value minus d minus the other distance we calculated. Right, and this is our kind of complex calculation for the compression and for the stretching for our spring. And then we have to check if we want to delete a spring, and we are going to delete a spring if the length of the spring is greater than the interaction radius. And then we can say listed springs delete with the key value. There we go. This is our adjust springs method. Luckily, the spring displacement method is a little bit simpler. It's not that much code, luckily. All right, then let's jump to the spring displacement. In here, we first need to calculate the delta squared. And this is just the delta time times the delta time. And then we have to iterate through all of the springs again. So let's copy this for loop here. There we go. And then we have a formula we need to calculate. And in this formula, we have a term. This will be our displacement term. And then we have a vector from the two particles. And we need to just scale then the vector. Well, we take the direction, normalize it, scale it with the displacement term, and then we are applying this displacement to the particle positions. Before that, we need to do something else. And well, first we need to calculate, of course, the direction. And this is the IY. Again, this time this is a direction, not a length. So this is Py dot position minus the neighboring one. Then we get the current distance out of this. So the distance is y dot length. And I want to just say if the distance is too small, then I'm going to say continue. This will prevent when the distance is going too small, then it's going to prevent some explosions I witnessed in the past in my implementation. And yeah, then we can calculate the direction vector. So, sorry, we can normalize the direction vector. There we go. And then we can now calculate the displacement term. So that displacement term is calculated by taking the dt squared times the spring stiffness. This is the K spring value you see in the paper. Spring stiffness times 1 minus the length of the spring. This is the Liy divided by h, and h is typically the interaction radius. There we go. And then we still need to multiply it again with the spring length again, minus the current distance of the vector. All right, cool. And this is now our displacement term. I think I'm put it like this. There we go. Okay. And then we can scale our RIY value with the displacement term. And this is the RIY, of course, and the displacement. And yeah, that's it. Actually, I'm gonna multiply this one by 0.5, because if you look at the algorithm, at the equation where we update the position, you can see that the displacement is divided by 0.5 or by 2. It's multiplied by 0.5 or divided by 2, and I'm gonna do this right here, and I'm gonna yeah, skip this step and calculate the vector. I'm gonna take it just, yeah, and I'm gonna calculate this in this line instead of doing it in the positional correction step, because then I'm saving a little bit of a code and some complexity. And then I can copy, and I'm not, and then I'm not can, I will not copy everything. I will then update the position of the particles, and this is then just a add and a sub, and here I'm gonna copy the position now. So at the end I copied anyway something, and here I'm at the displacement, the vector displacement, right? And then I'm gonna do the same thing for the other particle, and this is a subtraction, and that's it for our spring. Yeah, then of course we need to actually call these methods, and I call those in between the predict positions and the neighbor search, and I think I'm gonna move the neighbor search to the really top. So I'm gonna move this one right there. All right, and here below the predict position, I'm saying this dot adjust springs with the data time, and then this dot spring displacement with the data time. All right, and I'm gonna make sure now that we that I didn't make any mistake, and I'll be back in a second. Okay, and I found an error first. Here, right there in this line, we have to divide this by the interaction radius in the adjust springs method. Divide the length by the interaction radius, and I think, I hope this is everything now. Okay, yeah, and now I think we can go to the browser and check if it's working. So then save and refresh, and let's jump to the browser and WordPress. There we go. And this is our simulation now, and it seems that seems really cool. Yeah, it's working. Awesome. If I change the particle amount now, yeah, note I disabled the emitting, just spawning the square again. And now we have, well, I don't know how to describe that. Maybe a dough or something. But yeah, it's working. Cool. And actually now, I think I can now turn on the particle emitter. So let's try that. And I have to turn off the instantiate particles method. And there you go. So let's turn this one on. And there you go. You have our spawning, well, something. Cool. Yeah, we can even turn our emitter now still. Let me refresh this one, and yeah. Note that the particle at the spring stiffness is probably a little bit high. So I think I'm gonna change this one to, let's say, order plasticity, I don't know, maybe to 0.7, and the spring stiffness to 4. Let's see what's happening then. Right, and that's everything for today's episode. I wish you a really nice day, and I hope to see you in the next one. Bye bye.